Let's give everyone just a few minutes to drop on. Give them a few minutes, but a couple of seconds. Oh boy, got a full day today. Okay, I haven't tested out a lot of this stuff. It might just blow up on me. Uh-oh. Hope it doesn't blow up on me. Okay. So here we're not getting enough sound. Okay, let's get this show on the road. Let's get this rock and roll going. Welcome, tech artists from around the world. It is Friday, and it is 12:30 Eastern Standard Time. My name is Chris, and because it's Friday, that means that it is time for another episode of Tech Art Talk Live. That's right, gang. Now, last week, we started off by creating some interesting processes dealing with ray marching. What's ray marching? Well, ray marching is all about rendering a scene pixel by pixel by casting rays from the camera into the scene and then testing to see if that ray hits an object or not. And really, with that basic fundamental information and finding that distance of where it did intersect the object, what you can do is approximate a lot of things, and you can go in and create lots of amazing photos. Now, as an example of something like this, one of the big proponents of ray marching is a really brilliant guy named Inigo Quilez, and he is off in Spain. And I wanted to show you something that he created that is really pretty awesome. Yes, let's show this off. Okay, so let's go and show off this. Yes, okay, great. All right, so what you see here, folks, is what can be done with signed distance function. Now, a signed distance function, as a repetition from last week, is a function that returns either if positive, if the distance between the camera and the object is positive, or that means it's in front, or it returns 0 if it is on the surface, or returns negative if it's inside of the surface. And so, therefore, we have a very complicated signed distance function here for these elephants that Inigo created here. Now, this is really kind of impressive here. And if you ever have a chance to go about and check things out, I highly encourage you to go check out Shader Toy. It is a pretty amazing function. It shows what can be done with ray marching and just with shaders in general. Now, it's not all ray marching, but there is a lot in here, and it's a lot of very interesting stuff. So something very much to check out. Okay, so we've got things going with the ray marching here. Let me get rid of that. All right. Right, okay, let me get rid of here. Okay, I think this is good. Okay, yeah, sure, why not? So what we're going to do, this is part 2 of our ray marching. All right, last week we talked about what signed distance functions were, and we kind of gave an overall description of what ray marching in general could do. Okay, this week what we're going to talk about is, since we discussed what signed distance functions were, how do you actually shade them? Because last week we created a little quick shader, but we shaded a sphere, but it didn't have any kind of fall off. It didn't have any kind of shading inside of it. So that's what we're going to talk about this week, is how to actually pull off the shading inside of a signed distance function. And then also, as peculiar and as interesting is what to do with the transformation. Suppose you want to translate, rotate, and scale your objects. Now that image of the elephant that we saw earlier, there's a lot of transformation going on there with the sine distance function because they all started off as basically cubes, spheres, and probably tubes. Spheres, cubes, and tubes, probably, and maybe a donut or two. And the last section we're going to be talking about is the implementations. Now, you know what? During the implementation portion, when I was putting this, I realized that I have never broadcasted on how to actually program in HLSL. Now, HLSL and GLSL are the easiest ways of programming ray marching, but is not absolutely necessary. Now, I haven't tried to actually put this together inside of the material editor inside UE4. It would be kind of ugly, but I think it can be done, you know, and we'll show about how you would implement something like that inside UE4, but we're still going to be using HLSL, which is kind of a cheat, but HLSL kind of makes everything functional and easy. So that's what we're going to do. So as described earlier, we're going to talk about shading. Now, what is the first thing that you need in order to shade anything? Everything shading related, you know, whether it has Phong shading or even when you go into the complex PBR shaders, they've got to have surface normals. That means normals. Normals are those little arrows that are sticking up perpendicular to the polygonal surface. You got to have those normals. Without those normals, you can't render a surface. Now, traditionally, normals are stored inside of the vertices, and then during the rasterization process, they're interpolated across all the pixels. But what are we going to do now that there are no normals? Why are there no normals? Because we are not dealing with polygons anymore. We're dealing with volumes. And in fact, we could be dealing with abstract volumes that, you know, that don't really have any kind of face. You can't, you know, print them. You got to translate them into polygons so you can actually print them. So what are you going to do about that? Well, first thing you got to remember is that there's a concept out there called the surface gradient. Now, the surface gradient is the rate at which the curvature changes the fastest. Now, in this example here, we have the normal, and it's pointed right at a mythical camera here. Now, if we look at the normal here that's perpendicular, then as this normal moves closer and closer and closer to being parallel, to be pointing at the camera, you'll see that it actually starts changing faster as the closer it gets. So as we move down this line a little bit, it starts moving more faster and faster and faster until it gets to its totally fastest speed, and then that's where it figures that's where the fastest normal is. So if the fastest normals are pointed right at the camera and the slowest normals are pointed perpendicular to the camera, then you can kind of interpolate between that slowest normal and the fastest normal, between 0 and 1, and somewhere between 0 and 1, that's right. And so that is kind of the concept of how we guesstimate of where the surface gradient is. Now, we're going to be taking advantage of some, do I dare say it? Yes, go for it, say it. Calculus, yes. Okay, how do you implement calculus, gradients in calculus? Well, it looks kind of like this. If you have a gradient of some function, which in our case is a three-dimensional volume, it returns the gradient f. And that's what that little upside down triangle means. It means that it's a gradient. Okay, and so it is a partial derivative of the three major axes. So that means that the gradient changes with respect to x, with respect to y, and respecting to z, depending on which axis we're looking at, x, y, or z. Now, if you're not familiar with these partials means in calculus, don't worry about it. Because what we're going to do, we're going to say, leave that calculus at home. Don't even bother. Instead, try to do something simple like this. Now, this is much easier. So we're going to approximate what that gradient is. And so our normal is an approximation of f of x, y, and z. But notice here, here it is, f, x, y, and z, and minus f, x, y, and z. But notice here, but for the x component here, when we're doing the actual x component, we're going to add some kind of small number. We're going to call that number epsilon. So f of x plus epsilon minus f of x minus epsilon, that's going to give us our x component. And then we're going to do the same thing for the y. We're going to do y plus epsilon and subtract y minus epsilon. And that's going to give us our y component. And then we're going to have our z component is z plus epsilon minus z minus epsilon. Now, this looks like a nasty little function, but actually it's really, really pretty simple. Because remember, we're all dealing with sign distance fields. And so our function is really our SDF call. And if we were going to implement that in code, it would look like this. Okay. This is a lot of code, but really here it is. It's actually pretty easy. So we're going to say, we're going to return our normalized float 3. That means we're going to float in x, y, and z. So here's our x. So we have sine SDF, and then we have the position of x plus epsilon minus the sine SDF, the position of x minus epsilon. And then we're going to do the same thing for y. And then we're going to do the same thing for z. So it's always, the first side is the sign distance field of the component plus epsilon, subtracting of the sign distance field of the component minus epsilon. And that is how it generates our normals. Okay, and this is really all that there is to it. This actually computes the normal of any kind of surface of any SDF, and it does a pretty good job. Not too shabby, I'd say. Okay, so when we're implementing this into a shader and we actually want to make it work, there's a kind of a multi-step process that we got to follow along. Okay, if you're going to follow along, doing it the hardcore GLSL way, you could get lots of examples from shadertoy.com. Shadertoy.com is really pretty groovy, and ooh, we got a link here. What does the link actually give us? So let's go and check it out. Oh, it's not going to say. Okay, but I don't have this. But go check out this view. This NTSSR. It's going to be pretty good. So if we want hardcore GLSL, we would use ShaderToy. If we want hardcore HLSL, then what we're going to have to do is we're going to have to calculate the ray direction. And that means is we're going from the camera through the screen and into the scene. And so we're going to have to follow along what that ray direction actually is. And then we're going to have to calculate the shortest distance, and which is another word, we're going to have to use that ray march function that we described last week. Then we're going to use that to estimate the normal, and we just showed how to estimate the normal, so it's pretty good. And then we have to go and do the Phong illumination. That's right, folks. I have not told you what Phong illumination is. For those of you out there who are in the know, and you do know what Phong illumination is, bully! Excellent! Very good. But for the rest of you who don't know what Phong illumination is, not to worry. In the weeks to come, I will be showing you how to implement normal illumination algorithms using HLSL. And the Phong is pretty much the basic illumination model that's been been an industry standard for probably close to 35 years. Now, I don't want to go too much into the deviation of what Phong illumination is, but physically based rendering is a deviation from Phong illumination. Phong illumination approximates the specular component where the physically based component actually duplicates it. And there's a whole bunch to it. Tune in the weeks to come and we'll show you how to implement all of this inside of HLSL. Okay, we got to remember the lighting though information is because the light information is now wired inside of the shader. We're actually doing the lighting inside of the shader now. That means that the lighting information is going to be hard-coded into the shader. That is, unless you actually find some kind of way of piping that information from the environment into your shader, then you're pretty much going to have to hard code your light position, your light angle, your light orientation, your light color, all that good stuff. You're going to have to pipe that into your shader somehow. All right, now, if we're going to deal with this in UE4, then you got to deal with an unlit material, because remember, we're not using their shading algorithm. We're kind of like writing our own. This is kind of like definitely pirate shading here. All right, we're going to need the camera position. We're going to need our ray direction, which is nothing but the local position minus the camera position. Okay, nothing too complicated there. We need our light direction. We know which direction is the light headed. It's just kind of like more of where the light is actually pointed. If you're dealing with a point light, you don't even need to worry about that. Okay, what color are we dealing with? All right, so let's take a look at how this is implemented. First, let's show this off in, let's go into UE4 here. Okay, now we're in my ray marching level. So what I want to do is toss in a cube. Okay, we've got a cube in here. Nothing too exciting. We've got our cube, and so this is just to demonstrate that it is definitely a cube. So I'm going to go in here, and then I am going to drop in my material, and I'm going to drop it in onto my object. And voila, we've transformed it into a sphere. But if you look at it, something isn't right. I mean, it's a sphere, but it kind of looks egg-shaped inside, but it's still kind of round. And that's because it depends on the angle that we're looking at. Look at the shadows. We're seeing two different objects coming through on the shadow. Why is that? Because this is still a cube, and the cube is casting shadows. But what we're seeing is at any given time, we're looking at two sides of the cube. And they're both, and the sides, they're both projecting spheres. And so that is kind of the nuttiness, just to prove that we are dealing with a cube here. Look at that, check it out. We got two shadows here. But notice here that the lighting is off. So the lighting is evidently coming from the left-hand side, but we've got a dark side. Why is that? Well, remember what I told you before? The lighting is now being done inside of the shader itself, and so it's kind of hard-coded. Not to fear, folks. Oh, let's put this in here. I'll put this is my material instance. So I think, okay, well, there's the lighting look a little bit. I kind of like planned this out a little bit. So just to show you what this looks like, I'm going to look inside of my ray marcher here, or inside of the material here. And then here we have some little parameters that are exposed. If we wanted to manipulate the specular coefficient, we can manipulate the specular coefficient, not a problem. If we wanted to manipulate the ambient color, no worries. If it's green today, we want orange tomorrow. Okay, no worries. Now here is the light position. Now the light position has to come in as a vector. And so the light position is right now kind of like a little bit off of stage left, kind of like behind us. And so if I wanted to move that left and right, let's see, now my reticle here shows me that X is kind of going back and forth into the direction. So left and right is the Y-axis. So Y is green. So let's move green back and forth. So there we can see the light is moving back and forth here. Now if we want to go up and down, that is the Z-axis. And so we move that, and so the light is now moving up and down. And we're not going to see very much happening maneuvering inside of the X-axis, which is our depth, but you can see it moving over there and in the front. Okay, so there it actually is existing. Now, yes, we can manipulate the specular color as well if we wanted to be silly and nutty and say, okay, give this guy a green specular component and glare. Okay, then we have our green specular component. Not too exciting. So let's take a look what's inside of our ray marcher. Okay, here we are. This is really all it is. It's not very difficult. So here we have is our ray march shader, and then we had to tell it we want it to be unlit. and we wanted it to be masked too, so that we could deal with its transparency. Now notice here that I'm coming out of the ray marcher. I do have the opacity built into my alpha channel, and then I'm going to pipe that into my opacity mask. But otherwise, the color coming out of my ray marcher is just passing right into my emissive color. Now remember what I said earlier, we needed a bunch of things from the system in order to get this working. Now we needed the object or the local position. So basically, for every pixel that's being rendered here, we need its local position. And we need its camera position. And then when we subtract the local position from the camera position, we get the ray direction. All right. And we have the ray direction, and then we have our light direction. And in this case, we're just pointing it exactly right at the object. And then we have our base color, our ambient color, and our specular component. Not a problem. So those all go into our ray marcher. So let's take a look at this ray marcher. Now, I know that I haven't taught you folks the HLSL into this, but really this is all that the code that there is. So what we're looking at here is we're going to first get the depth. So we're going to get the shortest distance to the surface. And so we're going to check it out. Okay, if the depth is greater than some kind of maximum distance, then we're just going to return 0. He said don't return anything. Then, once we've got this depth information, what we're going to do is we're going to estimate our normal, and that's what this statement does here. And then with that, we're going to calculate our diffuse light. And this is something to take advantage of called Lambert's law. And I know we don't know, I haven't described what Lambert's law is for you folks. I'll do that in a couple of weeks. But we got our diffuse light, and then we're going to calculate our Phong light. And so that means is we're going to have to calculate our reflection angle, and then we're going to, with the reflection angle, we've got our specular light. And then our Phong lighting then is nothing but our ambient color plus our diffuse light plus the specular color, and that's all we're going to return is the Phong lighting here. So really not very difficult, not too complicated. So this is a kind of like a simple implementation inside UE4. Now if we wanted to go hardcore, then we would go into the hardcore HLSL. And let's take a look at what that would look like. Aha, there we go. Here we go, we're looking at hardcore HLSL. Yeah, guess what, gang? This is nothing but, as you can see, I've got a quad going into this. If we were to, this is nothing but just a quad going into this. So what we're looking at is a sphere inside of this. Okay, let's take a look at inside of what this function actually looks like. So it's a little bit ugly, but here we go. Here's the function that drives everything, called Phong illumination. And you'll see that it looks very, very similar to the UE4 implementation. First, we're going to have our light position, and then we're going to calculate our light intensity. And then what we're going to do is, wait, is this the Phong illumination? No, that's not quite it. The Phong illumination is actually calculating the Phong contribution, which is taking advantage of the diffuse and the specular. But oh yeah, here it is. Here it is. So here it is. We're first calculating the ray direction, and then we're going to have to calculate where the eye is looking at in order to get where the eye position is. For where's the camera's position, and then we're going to get our distance, which is the shortest distance of the surface. This is our SDF function. And then once we have that SDF function, then we're going to calculate the ambient component by, we're going to send in the estimated normal. And we're going to do the estimated normal on the result of our object. And then we're going to create the diffuse component and the specular component. And so therefore, all I'm going to return is the Phong illumination of the Ka, the Kd, and the Kd, plus the shininess and the new eye. Not too complicated. And it looks nasty at first, but that's because you've probably never seen HLSL before. But in the future, we'll bring that by. So there it is. We have just a very simple cube. Now, you're probably, why is it so colorful? Well, actually, instead of, I kind of cheated here. Even though I'm doing the Phong illumination on it, I never actually gave it a material color, so I wanted to just take a look at what the normals look like. And so what the normals are, this is kind of like a little bit like a bump mapping and normal mapping. And so what I'm doing is I'm taking the normal and then I'm just displaying what the color of the normal is. And so that's what we're looking at here. And you'll notice that we can't move around here, and that's because it's locked in here because we're not dealing with 3D geometry anymore. We'd have to put in some kind of transformations to actually go into this world. And if we wanted to take a look at what a cube looks like, yeah, there it is. There's my cube. Okay, and so the cube is done with a very, very similar function. And you'll notice here that the positive x direction is red, and the positive z direction is blue, and and the y direction, even though we can't see it here, it's going to be green. All right, so that is the basic implementation and the shading of how to do it inside of the code. Now, if you really want the code, contact me and I'll be happy to drop you the information. And I know I don't have it available here. Yes, kind of drop me a line and then I'll send you whatever information is necessary, I promise you. All right, so let's go ahead and get back to transformations. Okay, now as far as transformations is concerned, it's all fun and game until someone puts out an eye or they try to scale. That's right, gang. Scaling isn't so easy when it comes to signed distance fields. Translations, rotations, not too bad. So in fact, when translating and rotating is concerned, you just have to remember to kind of pre-transform the point, whatever, before evaluating the SDF. So you kind of had to do the opposite of the transformation to the point before putting it into the SDF. So suppose that you wanted to move your object up. So therefore you would subtract some position from that, and then as you subtract the position as it goes into the SDF, it will appear the object will move up. And if you want it to go in a downward direction, you would go and add information and it would go into the downward. So it goes in the opposite direction. Now here is my SDF with a little modification here. I put a sine wave inside of the X. So that means what it's going to do, it's going to move back and forth or up and down depending on which the order is. Yeah, so this is going to go up and down because here's X, Y, and Z, and this is zeta. And so we've got the sine of time, so it's going to go up and down very, very slowly. And that's really all that there is to it. Now, rotation is a little bit more dicey because you can't just add a rotation to it. What you have to do is you have to multiply the point by the rotation matrix. Now, if you remember, a bunch of weeks ago, a long time ago actually, I gave you the formulas for what the rotation matrices are. Ultimately, there are 3 rotation matrices, one for X, one for Y, and one for Z. And then you concatenate them by multiplying them across each other. And so that's what we're doing here, is we're going to take our point, and then we're going to multiply it by our Y rotation. And here, in this case, I'm going to rotate it by Y by a certain amount of time. And so what this is going to do is going to return a 4x4 matrix, and then we're going to multiply our point versus that, and that's going to give us our rotated. Now here's the weird part. Because we're dealing with matrices, HLSL does not have an inverse matrix function. It doesn't exist in there. Now, other libraries do support inverse matrix functions, but not HLSL. So what you got to do is just basically do it the opposite transformations in the opposite order. And that gives you the basic, and that does the essential equivalent. All right, so to show you what that all looks like, let me go ahead and turn this on. And there we go. So what we are doing now is we're rotating our object, and we're rotating and spinning our lights around the object. And so you see our object, we're actually rotating the object around, and so it's moving around here. And so what we see is the rotation of the lights and rotation of the camera around here. All right, and so that looks pretty good. And you'll see the same thing, it looks the same with the cube. Okay, remember what I said, that the X, Y, and Z axes, that the X axis was red, the Y axis was green, and the blue axis was or the Z axis is blue. So there we go. So that's how we're doing it. We're kind of like moving the camera around, moving the object around, and so that's how it's doing. All right, so what do we do then about scale? Okay. Before we get onto that, you might want to ask, are they still signed distance fields? And so the answer is yes, because the distance between the apparent vertices is still maintained. As long as you're maintaining that distance between vertices, you're doing okay. But I know what a lot of you folks are thinking. You're saying, like, okay, well, what about scaling? Now, scale, you could do things a little bit differently. And yet, that is true, that scaling is not a rigid body transformation. And so, therefore, the vertices don't necessarily need to maintain relative distance from each other. Okay, so what do we do about that? Okay, well, we can kind of take advantage of the fact that we're going to be doing the inverse transformation. And so that means is that we're going to have to be doing the inverse scale. So instead of like multiplying by a scalar number, we're going to divide by a scale number. So here's where the interesting caveat comes in. The resulting image is the same when you do these three things here. Now notice here, I've got my point, and then let's just say I wanted to scale my sphere up by 2. If we divide by 2 into the point, we've got this input, and this input. Believe it or not, these two inputs produce the exact opposite. I mean, not opposite, they produce the exact same thing. In fact, these things lie. They have no effect whatsoever. And it's kind of a curious situation. If you just move the you divide the point by the scale factor, and then if you multiply it by some kind of number, it doesn't really matter. Okay, but the true one is what you've got to do is you got to multiply, you got to divide the point before the SDF, and then after the SDF, you got to multiply it by 2. So in other words, so remember what we're sphere marching, and ultimately, it requires that the distance to be pushed forward as large as possible without overstepping. So here we have our situation of our camera. Our camera's looking at our SDF, and then we're going to try to figure out, okay, this is the furthest point, so therefore we're going to create a sphere around it, and then we're going to push forward that amount. And then here's our that, and we're going to push forward that amount, and there's that amount, and we're going to push that amount, and so forth. Okay, now we explained all this last week, but we want to require the distance the ray pushes to be as large as possible without overstepping. Okay, so if we undershoot, like we did, it's going to take more iterations and it's going to work much harder. But if we overshoot, now overshooting is really bad, because if we overshoot our volume entirely, then an entire volume is going to disappear altogether. And so that isn't cool. So definitely the lesser of the two evils is to undershoot. So what we're going to do is kind of modulate how much we go by. And so the solution is you're going to do the inverse transformation to the point, and you're going to transform the result of the SDF result. And so in other words, we're going to divide the scale into the point beforehand, And then what we're going to do is run it through the SDF function, and then we're going to multiply it by the scale. And then doing that in proportion will maintain actually the scale. This kind of works out when you realize it. So that means that the SDF is going to be moving, and then it's going to double the scale. So it works. It's amazing. It's uncanny, folks. So what you're probably wondering is that, okay, what are you going to do then with this non-uniform scaling? Well, remember, like for an SDF, we have this basic function of 2x squared plus y squared plus z squared minus 1. So that means we're going to end up with a kind of an egg-looking shape. And so that means that the x-axis is doubly wired. But remember that we can still, that undershooting still works. So therefore, when we're dealing with non-uniform scaling, or in other words, we have different x, y's, and z's, then we're going to take our point and we're going to divide through our x, y, and our z scale. And then what we're going to do is just multiply by the smallest scaling factor of whether the smallest x is x, y, or z. The smallest of those three. Then we're going to multiply the result of that by that. And that is going to kind of like move the ray along just good enough in order to get the kind of right distance we need. And that's how it's done. All right, so let's take a look at my shader graph again. All right, and so here we are. It's just moving along here. And let's see, do I have... All right, so there is an example of creating various shapes with sign distance fields. And that's how an example of how the sign distance fields can be used to cut away with each other. There's some basic simple rotations. Okay, there is our non-uniform distribution. And so all we have here is we've doubled the size of our x and just kind of made it kind of a wibble-wobby. And that's what we're looking at for. Remember, what we did was we divided the x, y, and z coordinate. We divided by 2 times x. And then we multiplied it by 2 times x at the end once it came out again. Okay, there's a tube. There's a box with rounded corners. There's a donut. And there is a cone. Okay. Well, that one is a plane, and that one doesn't look as good. But here we have is a whole bunch of rounded cubes, and they go off into infinity, depending on which direction that you're looking at. All right, and there is our final little bit of animation there. Okay, remember, if you want to get more to figure out how to model with sign distance functions, my suggestion is to go check out Inigo Quilez's website. And here's a link to his website again. And so it will show you how to create sign distance functions in order to get all of that working. And his stuff is really very interesting. And in fact, I want to bring up a little bit more of his stuff inside of this shader tool. Ooh, look at that. Descending down the worm tunnel. Very cool. Gotta love these SDFs. All right. Okay, so I promised you that I was going to teach you folks how to do HLSL and program shaders. Well, I sort of lied, because that's going to take more than 1 week, and there was something very, very interesting. I just read a book called Getting Naked, and it's a very, very interesting book. And so therefore, what we're going to talk about are the basic fears that tech artists have to deal with. We're going to kind of interject that in as a kind of a one-shot next week. And so what we're going to do is we're going to get naked. If you want to find more about fears of being a tech artist and getting naked, tune in next week, and we're going to talk all about that. Very interesting. And we're going to do that right before going on into shader programming. Okay, remember at GDC, if you happen to be bopping by GDC this year and you happen to be going to the teachers conference, the teachers which I'm sure you're all standing in line to get in line right now. Right after the UE4 and the Unity release lines. Yeah. But if you happen to find yourself into the teaching forum, go check out GDC 21 on July 21st at 1:20 Pacific Standard Time. That's San Francisco time. Go check out Object-Oriented Python Crash Course using Houdini. Yep. Yours truly will be teaching that one, and I'll be teaching you ultimately what I kind of taught before, but kind of like in a half hour rather than in 6 weeks, how to program in Python and how to use Houdini as a good interactive editor for the Python. All right. If you like what you saw today, go ahead and subscribe to this YouTube channel, or you can go check me out. I'm Chris Rhoda. You can check me out on Facebook and on LinkedIn. Otherwise, you go check out the website, Art EDU, and check out the Facebook and the LinkedIn website. And if you're sitting around there and you're actually going to the Art EDU website, go opt in and click the little opt-in button here and leave your email address, and then I will send you out information as the information comes out of everything wild and wacky going on here with Art EDU. Well, thank you very much for joining me today of my deep dive into ray tracing. Last week and this week have been a pure pleasure, and I really enjoy talking about it. And I hope you'll be able to join me next week when we're talk about fears that all tech artists have to deal with and getting naked. So until next week, arrivederci.